Hi class, welcome to the next section. Today we're going to talk about polynomial functions and their graphs. We are going to talk about how to graph a polynomial function by hand given the information we have already. So this is a common theme that happens in a calculus course. As a preview, in Calculus 1 you learn a lot more tips and tricks for analyzing graphs, and part of that is learning how to graph a polynomial function by hand in more depth than we will today. So today we'll be able to do a pretty good job of being able to graph a polynomial function. We're going to analyze their graphs quite a bit, and again, you do this again in Calculus 1 but into greater detail. So let's go ahead and get started. So we're going to introduce some new notation. We're actually going to introduce some calculus notation. So this is actually very early to be learning this notation, so it just makes things go a lot smoother and a lot easier. So it'll be very helpful for us for talking about functions and quite a few other things also as we progress through this course. So let's just kind of review what a polynomial function is. A polynomial function has the form p of x equals a n x to the n plus a, this is subscript n minus 1, times x raised to the power of n minus 1. So as you see, the subscript and the powers, they coincided with each other. And we do this continuously, right? Decreasing our subscript and decreasing our power until we get to 0, right? So we have a2 x squared plus a1 x1, so this is the power of 1, plus a naught times x to the power of 0. Remember, x to any power, or I'm sorry, anything to the power of 0 is just 1, so we don't write a 1 or x to the 0 power, we just write the value a naught. So again, remember, these things are called coefficients, and we have a couple of very special things that are going on here. So again, I think we talked about this in chapter 1 a little bit as well, so this is just a little bit of a review. Here, instead of calling it f of x, however, we're calling it p of x, p for polynomial. Okay. The degree of this polynomial is the highest power present, which is n. So I would call this an nth degree polynomial. The coefficient that is attached to the nth power variable x is called the lead coefficient, right? So the first coefficient that shows up is the lead coefficient. We've talked about this before as well. If this coefficient is 1, we call this polynomial monic, right? So it has a term of 1 in the front. An times x to the n, this whole thing right here is the leading term, right? So the first term, this is the highest power, nth power. An is the lead coefficient. So lead coefficient, leading term, okay? A naught is the constant term. As you can see, there's no variable part associated with it, so this would just be like 3 or 5 or pi or something to that effect, okay? Each a sub I, that means a n minus 1, a n minus 10, a2, a1, each of these are just coefficients, okay? So sub I is just a general index, right, for any one I that I decide to choose. And each of these things is considered a term. So again, I is just a general term. So it could be the n minus 1 term, it could be the I 12th term. It's just a general term where I is the index. Okay. So let's talk about graphing polynomials. Okay. So when we're graphing polynomials, we have to take a lot of things into consideration, right? One of those is the degree of the polynomial. The degree of the polynomial tells us what the general shape is, right? We need to know what the sign of the lead coefficient is. So if an is positive, our function looks like one thing, depending on what the degree is. If an is negative, depending on our degree, our graph looks like something else, right? The zeros are very, very important. They give us a lot of information about the graph. So again, when I say zeros, I mean the x-intercepts, but we are interested in the y-intercept as well, okay? So these are the things at this point that are the most important to us. When we get into Calculus 1 and we start talking about polynomials and analyzing the graphs a little bit deeper, there's a lot more things of interest. Well, not a lot, there's only a couple, but it helps us to be a little bit more accurate when we're trying to graph these functions. Okay, so we also need to evaluate the polynomial at a few values that are between the x-intercepts, the zeros, to help us get a clear picture of what's happening in between the values that we have known information for. Okay, so the degree. Okay, let's talk about how this affects our graph. What this does is it really just tells us the general shape of our graph. So if our degree is 1, right, a linear equation, we just have a line. Notice that the max number of zeros possible is just 1. There's only one time possible that I can cross the x-axis, right? Even if I shift this around, there would only be one point where this line crosses the x-axis. Okay. If I have a quadratic, right, my degree is 2, and the maximum number of zeros is 2. It could have 0 zeros, 1 0, or 2 zeros, right? So the max would be 2 points of intersection on the x-axis. Okay, do you notice pattern developing yet? If I have a cubic, the max number of zeros would be 3, right? 1, 2, and 3. I can have less than 3, but I cannot have more than 3, right? So if I have a fourth degree polynomial, what do you think the max number of zeros is? 4, okay? So your degree matches the maximum possible number of zeros that you can have, okay? So 1, 2, 3, 4. For a fifth degree polynomial, the max we can have is 5. 6 is max possible 6. 7 would be 7, etc., etc. So that's one thing that we notice as we look at polynomials of increasing degree. What are some other things that you notice? Okay, well, let's look at this. All of my odd degree polynomials have something in common, and all of my even degree polynomials have something in common. I'll give you a second to look at it, see if you can figure out what that is. Okay, so if you didn't notice, for a standard form of one of these polynomials, all of the odd functions, all of the odd degrees, resemble in some sense a straight line, meaning that I start at the lower bottom left corner and I end at the upper right side, right? From left to right, it increases. From left to right, overall, it increases, right? I start at the bottom and I end at the top. Here, overall, I'm increasing, okay? So it comes from down and it moves its way up. For all of the even functions, right, all of the even degrees, it has somewhat of a U-shape, okay? Somewhat of a U-shape, somewhat of a U-shape, right? So it's basically a U-shape with some squiggles in the middle. A U-shape with some squiggles in the middle, right? For the odds, it's basically a line with some squiggles in the middle, right? A line with some squiggles in the middle. So that's the difference between an even degree and an odd degree polynomial. The general shape of the graph looks like this, right? So as I go very, very negative, my function increases. As I go very, very positive, my function increases, right? For an odd, as I go very, very negative, my function decreases, gets very, very negative. And as I go very, very positive, right, larger and larger values of x, my function gets larger and larger in value. Okay, so we're going to bring that around to a more mathematical notation, right? For odd degrees, as x gets large, the function gets large. As x gets very negative, right, large in the negative direction, the output becomes large in the negative direction, right? Towards negative infinity, towards positive infinity. For even functions, even, not functions, but even polynomials, as x gets large, the outputs go to infinity. As the inputs go towards negative infinity, the outputs go to positive infinity. Okay, so what we call these are the end behavior, right? So again, notice that the maximum number of real zeros matches the degree of the polynomial, which we stated already. when n is odd, the polynomial acts like a straight line with some squiggles in the middle, the zeros that we are interested in. P of x comes from the negative direction with negative values, but is increasing overall. And the ends with positive values and continues to increase, right? So starts from negative and it goes towards positive for the odds. Okay. We call this the end behavior of the graph. Okay, so as x gets large, what does our function do? As x gets large in the negative direction, negative 1,000,000, for instance, what is the function doing, right? So we call this the end behavior because we're talking about what it does at the large ends of the graph, either positive infinity or towards negative infinity. Okay, so in simples, we say that as x gets more and more negative, P of x gets more and more negative, right? It tends towards negative infinity. And again, these are for the odds. As x goes towards negative infinity, the outputs of my odd degree functions gets more and more negative. It goes towards negative infinity as well. Okay. Right. So again, in symbols, as x gets more and more negative, P of x gets more and more negative. It tends towards negative infinity. So we say P of x goes towards negative infinity as x goes to negative infinity. And again, we are talking about the odd functions here, right? We're only talking about when n is odd, right? When n is odd, the polynomial acts like a straight line. As x gets more and more negative, the function also becomes smaller, right? And when we look at x as it increases, we see that as x gets larger, P of x gets larger as well, right? So the outputs become large as our inputs move further and further along in the positive direction. Okay, we call this the limit of the function as x goes to either positive infinity or negative infinity. So the behavior of our function as x becomes large in either direction, either very, very positive or very, very negative, we call it the limit of the function. The limit of the function as x goes to infinity or to negative infinity is the end behavior of our function. So what our function does as we go to either extreme for our inputs. Okay, so we have a special notation. So this is calculus stuff that we're talking about right now. Okay, so I'm just giving you like the quick and dirty version. In calculus, we developed this a lot, but if you understand what this is now, it'll be a lot easier when you get to the calculus course, right? So the special notation for this looks like this. We say the limit as x approaches whatever value it is that I'm interested in of P of x. Okay, so in this case, we're looking at as x goes to either positive infinity or negative infinity. And this is a value, okay? This will equal infinity or negative infinity, okay? Sometimes this will equal an actual value, right? Not for polynomials, it doesn't. But when we get into the rational functions, we'll talk about that. It will equal an actual value. So we're going to use this notation a lot in this course, okay? So let's talk about this, okay? So for an odd degree polynomial, the limit of P of x as x goes to infinity is infinity. So let's just backtrack real fast. So again, we're talking about an odd. As x goes to infinity, my function goes to infinity also, right? This is only for the odd. So as x goes to infinity, my function goes infinity. So the limit as x reaches infinity of my function is infinity because my function is increasing as my x is increasing. Okay. All right, so again, this has the same meaning that my function goes to infinity as x goes to infinity. So that's how we read and understand this notation. So it's a smaller form of saying this, okay? Now there's a lot more that goes into it. It's a lot more versatile than just this, but this is, our introduction to this, right? So if I say that the limit of P of x as x goes to negative infinity is negative infinity, that's the same thing as saying that my function gets very large and negative as x gets very large and negative, right? So like if I plug in negative 1 million, I'll get out negative 1 billion, right? So as I plug in very large negative numbers, I get out very large negative numbers. That is what this notation is saying. So as x goes to this value, right, continues to get large and negative, my function continues to get large and negative as well. Okay, so this is for odd, right? So as x continues to get large, the function continues to get large. As x becomes very large negative, the function becomes very large and negative. It's different when we have even polynomials, right? It resembles a quadratic function. So even when x gets very large and negative, I still have positive outputs, right? My outputs just keep getting larger and larger and larger. So when I have very large values to plug into my function, I just get very, very large outputs out as well, right? So my end behavior for an even polynomial, an even degree polynomial, is different than that of an odd degree polynomial, okay? So the leading coefficient is also going to influence this behavior, because remember, if the leading term is positive or negative, it flips our graph over the x-axis, right? So it changes what these end behaviors are, right? So for instance, for an even polynomial, an even degree, if I'm going really, really large and getting really large values out, or if I'm going really, really negative and getting positive values out, a lead coefficient that's negative will flip that graph over the x-axis, right? And all of these values will be negative in that case. So then what would happen is as x goes large in the negative direction, I have negative outputs that keep getting bigger, right? And as x goes further in the positive direction, I have outputs that continue to get large but in the negative direction as well. So that leading coefficient will change if it's negative, right? So again, remember, R means all real numbers. Negative here means only the negative real numbers. So if an is negative, then the graphs presented above are going to flip across the x-axis and they're going to change their end behavior. So this is just a table. I know it looks really, really ugly, especially since you just learned this notation, okay? But it's very useful because it separates us. If I have an odd function and my leading coefficient is positive, it behaves like we're used to. When x gets very negative, my function gets very negative. When x gets very large, my outputs get very large, right? That's for odd functions like lines, cubics, things like that, right? If it flips over the x-axis, right, so my leading coefficient is negative, then the signs change. As x gets very negative, instead of it going to negative like it should, it'll be positive, right? And as x goes in the positive direction, I get out more and more negative values, right? Same thing here for an even degree. If my lead coefficient is positive, no matter which direction I'm going, my function tends to get larger and larger in the positive side. If I flip it over the x-axis because my lead coefficient is negative, then no matter which direction I go to the extreme, positive infinity or negative infinity, my outputs just get more and more negative, okay? So that's how we read this. It just makes the notation a little bit simpler to read. So again, you have to make sure you're looking at what x is doing, and then this represents what your function is doing, okay? So now let's talk about zeros. Okay, so the zeros of a polynomial are very important to us. Yeah, they're known values. It lets me know, when my output is 0, which has very important connotations when we're looking at the application. But it really, really helps a lot when I'm trying to graph, okay? So they help us to shape the interior portion of our graph. So I already know what my ends look like because I can analyze the end behavior based on the lead coefficient and on the degree of the polynomial, right? I know what the overall shape of my graph is going to be. The zeros help me to plot what these things are doing, the inside, right? So I know the ends, I know if they're going up or down or, whatever's happening, but the zeros allow me to understand what's happening in the middle of my graph, okay? So, So when we look at the zeros of a graph, what we're really looking at is the multiplicity of the zero, okay? The multiplicity. The multiplicity is the number of occurrences of that zero. Okay, the multiplicity is an actual value. When that value is even, our graph does one thing. And when that value is odd, our graph does something else. Okay, so again, the multiplicity is the number of times that that zero is repeated for that polynomial. So here we'll call our zeros lambda. So let's say that lambda is a zero of my polynomial p of x. So if I plug in lambda to my function, to my polynomial, I get out 0. Okay. Let's say it has a multiplicity of m. That means that lambda is a 0 m times. So there's m factors of lambda. Okay, so this is what it looks like, because if I plugged in lambda, lambda minus lambda is 0. So if it has a multiplicity of m, that means x minus whatever that 0 is occurs as a factor m times. So x minus lambda, x minus lambda, x minus lambda, m times. So I can rewrite that as x minus lambda to the mth power. Okay, it's just a repeated root. M tells me how many times that root is repeated. That's what's going on here, right? So these are all factors of my polynomial. So if lambda has an odd multiplicity, so if m is odd, then p of x crosses the x-axis at x equals lambda, right? So at that value, at that 0, the function crosses the x-axis if my m is an odd number, okay? If m is even, then it bounces off of the axis at that point, okay? So for instance, here we have two cases. One, it crosses, and the other, it bounces off. Since it's coming from the top, it bounces off and it continues to stay positive. If it was coming from the negative, it would bounce off and it would stay negative. So this is an odd multiplicity for this 0, which we'll call lambda 1. This we'll call lambda 2, has an even multiplicity. It bounces off of the axis. This one is odd. It crosses the axis. Okay, so that's what the multiplicity does. It tells us what the shape of my graph does in the middle, if it crosses or if it bounces off of the axis. Okay, this is the limit of my function as x gets large, right? So as x is getting large, this arrow indicates that my function continues to get larger. So the limit of my function as x gets large is my function continues to get large. Same thing here. As I go more and more negative, right? As x goes towards negative infinity, p of x equals negative infinity. It gets smaller and smaller and smaller. So this little graph here is a perfect representation of these last two very long slides, right? It talks about the limit as we go to positive infinity, negative infinity, and what an odd multiplicity and an even multiplicity means for my function. So now let's talk about local extrema. Local extrema are local maximum or minimum values. Okay. If p of x is of degree n, then our polynomial has at most n minus 1 local extrema. So if our polynomial is 5th degree, we're going to have at most 4 local maximins. Okay, so again, let's come back to our graph here. Okay, so here n was 1, there's no local max or mins. Here my degree is 2, there's only 1 maximum local max or min. Here degree is 3, at max I can have 2. Okay, so again, these are at max, right? Degree 4, at max there's 3, 1, 2, and 3. Degree 5, there's at most 4, 1, 2, 3, 4. And again, that's because of the way the graph goes, right? I can have at most 5 zeros. So there's that many times where the graph changes direction, right? Giving me 1, 2, 3, 4 at most local max and mins. Same thing here. At most, there's 5. 1, 2, 3, 4, 5. So there can be less than that, especially if there's repeated zeros, because then I'm bouncing off or crossing, so there's less distinct zeros, so there's less of this wiggle that happens in the middle, right? So let's come back to where we were past here. We're talking about max event. So here's my example. We are going to graph this crazy long polynomial by hand, we're going to show all work. So at this point, we can get a pretty decent representation of my graph. And there's ways to make it even more exact. Once you get to calculus, you can graph this thing pretty much exactly by hand, so without the use of a calculator. So you might be saying, well, if I have a calculator, why would I want to do this by hand? Because it's going to help you to understand how polynomials work. That's why, right? Not only that, but also once we start to get higher into our math, into calculus 2 and 3, you're not going to always graph your functions. A lot of times they're very hard to look at, and a simple analysis is a lot faster than trying to plug in all of your values. Okay, so by hand, let's show all of our work. So first we would like to figure out what the degree of the polynomial is. So I have a 1 degree times a second times a third. So if we were to multiply all of these out, this would just be an x. If I expanded this, I would get an x squared. If I expanded this, the highest degree would be an x cubed. And then as I multiplied all those across, I would get an x times an x squared times an x cubed max. So the max degree I can get from multiplying this out is 6. Okay, so the degree here is a 6-degree polynomial. I do not need this to be in standard form in order for me to do all the stuff that I need to do to it. In fact, having it factored is way easier. In fact, if this was in standard form, the first thing we would do would be to factor it. Okay, so now you might be saying, factoring a 6-degree polynomial? How am I going to do that? Well, that's what's coming up in the next couple of sections. We'll learn how to factor literally any polynomial that is factorable. Okay, so here, the sum of the powers, since it's in its factored form, is what the degree of this polynomial is. Okay, so if you don't remember, let's just think about what does a quadratic look like. All right, a quadratic in factored form would be something like x minus 1 times x minus 2. There's 2 factors there, right? Or it would be just something squared. So if you take all of your factors, in this case there's 6 factors that have an x in it, that's the degree of the polynomial. Okay, so this means that the general shape is a U shape. So again, it's going to look something like this. Okay, however, whether they both point up or both point down depends on the lead coefficient. And then the number of squiggles that are actually in the middle really depends on what the factors look like, right? So again, this is the max number of zeros that we'll see here. All right, so again, let's come back to our, here we go. So in general, it's a U shape. Here you can see the lead coefficient is negative. So it'll be more like a hill than a U. Right, so the lead coefficient is negative, so we know that the end behavior is that both ends of the graph tend toward negative infinity, right? So as x goes towards negative infinity, our function outputs will go towards negative infinity, right? As our x values get very, very large in the positive direction, our output values of our function will go towards negative infinity as well. Okay, so again, we're going to kind of keep track of everything and then put them all together at the end into a graph for ourselves, right? So now I know the end behavior. I have the degree, so I have a general shape, right? The general shape and this value let me know what the end behavior is, right? So again, the general shape is going to be a hill. So now I can start to focus on my zeros, right? So it's going to be a hill, not a valley like a U, right? My y-intercept is what happens when I plug in 0 everywhere. So if I plug in x equals 0, I basically get negative 1/2 times a negative 1 times a 1 squared times a negative 2 cubed, which will get me negative 4, right? So this will be a negative 8 times a negative 1 is a positive 8 divided by negative 2 is a negative 4. So this is very easy to calculate as well. So I have my y-intercept. I have my end behavior, okay? I know that my graph crosses the x-axis at x equals 1 and x equals 2 because x equals 1, the 0 to this guy, has an odd multiplicity. This guy right here has an odd multiplicity as well. Multiplicity is 3. So these are the points where it crosses, okay? Again, odd multiplicity means it crosses. Even multiplicity is where it bounces off. Okay, and it's going to bounce off the x-axis at x equals -1. All right, so if we put all this together, okay, I don't have to go too far because my zeros are located around 0, right? -1, +1, +2, so I don't have to go too far on my x-axis. So what I do know is that after the zeros that I do have, I go down, right? So from the smallest 0, which is -1, I'll go down, right? From the positive, the largest 0, I go down. Okay, so -1 and +2. So I know that those are my zeros. I know my y-intercept, okay, and I know my end behavior. I know it goes something like this, okay, because these are, now I'm only interested in the middle stuff, right? So I got my end behavior. I know I go down and down because it's generally a U shape. I know I'm going to have to cross the x-axis at this point. So now I need to focus on what happens in the middle, okay? So I know that I'm going to cross the graph at 1 and 2, but I bounce off the graph at -1. Okay, so at -1, I bounce off the graph, so I'm not going to cross. It's not going to go up. It's going to come here, and it's going to hit the x-axis and bounce off and come to -4. Okay, at 2, it's going to cross, and then at 1, it's going to cross again. So I know that I have to go up and I have to go down. I know that this bounces off and comes here, so it's going to come around this way, right? So again, because of what happens on the zeros, I can figure out what happens here. I know at -1, just so that we repeat ourselves one more time, at -1, I bounce. At 1 and 2, I cross because of the multiplicity here, right? So zeros, y-intercept, my end behavior, because after the zeros, there's nothing else that happens to my function. So I have my end behavior. I know this bounces, okay, and it has to come down and cross 4. And then the next thing it does is it crosses 1 and crosses 2 again. So it has to look something like that. So that's me just trying to put everything together. So this is my rough graph. I have no idea what this actually looks like. So let's compare this to the actual graph. Okay. Pretty close. Okay, pretty close. So this is my ugly version that I guessed because I just know what happens at the end. This is what exactly happened. So if I wanted to be a little bit more accurate in my guess, I would have evaluated some points of my polynomials. Just plug in a couple points to see what happens. So for instance, maybe I plug in a value in between -1 and -2, -1/2 for instance, plug in a value in between 1 and 2, maybe 1.5, and then maybe 2.5, just so that I have a better idea of what happens, because obviously this gets very, very negative very, very quickly, right? So it doesn't come out as far. So that's what happens when you just say, oh, you know, I know some stuff that happens. Also, if I plugged in the value right in the middle, I would know how far up I have to go. Because what if this went super high and then came back down, right? So I just guessed that it went low, and I was pretty good in the guess, but look what happens. It also does a little dip thing, okay? Here, that matches up pretty well, okay? So just plugging in a couple of values could have allowed me to be just a little bit more accurate, right? So if we wanted to do our graph to look more like the actual graph, evaluate the polynomial at a couple of the interim points just so that I know what will happen, right? So some easy points like -2, -1/2, 1/2, 3/2, and 3. So the easiest points that are around the values that I know is happening. And I could have got something a little bit better, but we did pretty good for the knowledge that we have being applied to graphing by hand.